Alright, so in this video I'm gonna be explaining this article, Domain Adversarial Training of Neural Networks, which was in 2016. We introduce a new representation learning approach for domain adaptation, in which data at training and test time come from similar but different distributions. Our approach is directly inspired by a theory on domain adaptation, suggesting that for effective domain transfer to be achieved, predictions must be made based on features that cannot discriminate source and targets. This approach implements this idea in the context of neural network architectures that are trained in labeled data from source domain and unlabeled data from target domain. As the training progresses, the approach promotes the emergence of features that are discriminative for the main learning task on the source domain and indiscriminative with respect to shift between domains. We show that this adaptation behavior can be achieved almost any feed-forward model by augmenting it with few standard layers and a new gradient reversal layer. So the resulting augmented architecture can be trained using standard backpropagation and stochastic gradient descent. We focus on learning features that combine discriminative and domain invariance. This is achieved by jointly optimizing the underlying features as well as two discriminative classifiers operating on these features. The label predictor that predicts class labels and is used both during training and test time, and a domain classifier that discriminates between the source and target domains. We consider classification task where X is the input space and Y is the set of L possible labels. Moreover, we have two different distributions over X, this product space. We call the source domain D sub S and target domain D sub T. So the goal of the learning is to build a classifier either with a low target risk, such that the probability of eta of X is not the label, is not a particular label. So we have L labels and X is just the input space. We can define the edge divergence between the two domains, source and target domains. And the edge divergence relies on the capacity of the hypothesis class to distinguish between examples generated by source from examples generated by target. So we can compute this empirically instead of just this one, which is intractable. We compute it empirically, and I is always indicator function. If the predicate is true, it becomes 1, otherwise it becomes 0. So Ben David in 2016 suggested that even if it is generally hard to compute that empirical measure that we talked, we can easily approximate it by running a learning algorithm on the problem of discriminating between source and target examples. So we construct a new data set where the examples of source are labeled 0 and the example of target are labeled 1. then the risk of a classifier trained on a new dataset approximates the mean part of equation 1. So H is a hypothesis class of VC dimension D with probability 1 minus delta. And this is the empirical source risk that you see. So there is a bound for the target domain. So the heart of the approach is to design a domain regularizer directly derived from edge diversions. So we view the output of the hidden layer as the internal representation of the neural network. We denote the source sample representation as this one. So given an unlabeled sample from target domain, we denote the corresponding representation. The empirical edge divergence of a symmetric hypothesis class between source and target is this. So let us consider H as the class of hyperplanes in the representation space. Inspired by the proxy A distance, we suggest estimating the mean part of equation by a domain classification layer that learns a logistic regressor parameterized by a vector scalar pair that models the probability that a given input is from source domain or the target domain. Hence, the function G is a domain regressor. And I have a playlist for GANs and generative AI that I've explained GANs, conditional GANs, and all of these things that we always want to create a generator that can fool the discriminator, so that, for example, we have many applications. For example, you want to create synthetic images so that it fools the real images. You want to create some fake images or synthetic images that can fool, or many applications. But it has also many applications in domain adaptation. So recall that for examples of source distribution, the corresponding labels are known at training time. And for target domains, we do not know the labels at training time. And we want to predict such labels at test time. This enables us to add domain adaptation term to the objective function. So we have this regularizer. So it seeks to approximate the edge divergence. So we first note that we can rewrite the complete optimization objective like this. Now we are seeking these parameters that delivers saddle point. So we are minimizing it, but also maximizing with respect to different set of parameters. So everything is standard. So here we update the domain classifier. This is the regularizer that I was talking about, and everything else is just standard. So we have these update rules, and so this is the architecture. We have feature extractor, which is common. But the novelty of this paper is just this gradient reversal layer. Because not only we want to classify a label L, we also want to have a domain classifier. But so the architecture includes a deep feature extractor, the green one, and a deep label predictor, This is the deep label predictor, the blue one, which together form a standard feed-forward architecture. Unsupervised domain adaptation is achieved by adding a domain classifier. So this red one is the domain classifier. Connected to the feature extractor via a gradient reversal. So as I said, this is the novelty of this paper, that multiplies the gradient by a certain negative constant during backpropagation based training. Otherwise, the training proceeds standardly and minimizes the label prediction loss and the domain classification loss. So this gradient reversal, ensures that the feature distribution over the two domains are made similar. So in the context of GAN's generative adversarial networks, you can think about this as your generator. And you see it is shared, so we have just one generator, but we have many other complex networks that few or even nothing is shared, that there are different architectures. This is the simplest architecture for domain adaptation that comes to my mind, to any person. So we are just trying to have a generator that can adapt to the target. So we can formally treat the gradient reversal as a pseudo function defined by two equations. So we can then define the objective pseudo function, and that's it.